Now we are going to do a quick recap of how to find the shear force and the bending moment at any given section of a beam, and then we are going to look at some fundamentals, right? So if we take a beam, for example, let me draw a beam here for you. Let's say we are looking at a simply supported example of a beam. A pin support at one end and a roller support at the other, and for the sake of discussion, let's say this beam has a variety of loading. Maybe it has a uniformly distributed load, maybe it has a point load somewhere over here, maybe at a particular point it has an applied bending moment within the beam itself. Now when we are going to find the value of the shear force and bending moment at any section of this beam, so if I have to go and at my section of interest, maybe at a distance x from say the left end over here, suppose I am trying to find the shear force and the bending moment at this distance x, right? So to find the shear force and the bending moment, as we did in the introductory lecture on this topic, what I can do is that I can only consider the left hand part of the beam. So if I'm considering only the left hand part of the beam, what I will have the pin, I will have the uniformly distributed load, and where I have cut this particular section, here I am going to have a shear force V and a bending moment M. Now remember that this direction of the shear force and the bending moment which I just drew over here is the convention for the positive shear and the positive bending. Why? Because the V tries to rotate your beam in a clockwise manner and your bending moment M tries to bend your beam into a trough. It causes a sagging kind of a movement that is there, right? So to find this V and M, essentially what we have to do is that we just have to do the equilibrium of this left hand part. If you consider this left hand part over here, here you have a loading, here you have a condition over here which will have a kind of if I just have to do it, will have a reaction, right? Essentially it has a force, and all you are trying to do, you are set to find this V and M, and what you have marked over here is your positive convention for V and a positive convention for M. Now after solving the problem, your V might come out as negative, M might come out as negative, which is fine. It just means that what you have marked, your actual shear force actually is working out in the opposite direction. This is exactly similar to when you have a structure and you have a different types of load, and you don't know that whether the reaction forces are going to point vertically up or down. You simply mark both of them maybe vertically up, and the problem works itself out for you to tell you what is going to be the direction. So what you are marking prior to actually finding the values are the positive conventions. The values may come out as positive, which means what you have drawn is in the right direction. The value may come out as negative, which means what you have drawn, it actually should point in the other direction, right? Now, so this is one of the ways in which you are going from the left to the right. You're cutting this section over here. You can do a similar equilibrium of the right hand part. So as I drew this section over here, I could have segregated the beam into two parts. This is my, let's say, left part, and this is the right part over here. So the first figure which I drew over here, this is the equilibrium of the left part. Now I can have an equilibrium of the right part as well. So let's just quickly draw the beam on the right part from this all the way to here. So on the right part I have the load acting, and then I have a moment maybe, right? And remember again the positive convention for shear, if you are taking that right hand part that you're where you're taking this particular section, is that your V points vertically up and your M points like this, right? Similar nature of action, your shear force V tends to rotate your element in a clockwise manner, and your marked positive convention for the moment M turns your beam into a sagging effect. So it causes the beam to bend into a trough, right? Again, for this particular case, as you can tell that whether you're finding the M and the V from this the left hand part, or whether you are finding the m and the v from this right hand part, it must come out to be one and the same, because your entire system is in equilibrium and you've cut a section where the v and the m, whether you're calculating from the left hand side or the right hand side, it should come out as one and the same. What you have to keep in mind is that how you have initially marked. So always when you're solving problems on shear force diagrams and bending moment diagrams, when you're cutting a section, always mark depending upon if you're looking at the left hand side. If you're looking at the left end over here, that means your v comes down, m acts like this. Or you're looking at the right hand side, and if you're balancing, or if you're applying the equations of equilibrium of the forces and the moments on the right hand side, your v points vertically up, m goes like this over here. Essentially, v, the positive convention of v is it tries to rotate your beam or your element clockwise, and m tries to make your beam smile. It tries to make your beam act like a trough over here, right? Okay, now in addition to this, so this was mostly the recap part. Now in addition to this, some very basic fundamentals which we have somehow looked at a little bit in our introductory lecture. For example, suppose if you have a beam, so let's draw a simply supported beam again. So if we draw a simply supported beam, right, suppose you have a pin support at the left end and a roller support at the right. Now, regardless of what kind of loading that you have, as long as the loadings are intermediate between the left support and the right support, in a simply supported beam, or when your pin ends and the roller ends are at the very ends of the beam, you will not develop any bending moment. And what is the reason for that? Remember, as long as it's a pin support or a roller support, it allows for some amount of rotation. And when you have rotation, that means the corresponding force, right, in this case the moment, does not develop. So again, another way to think about it is that if you are not allowing a particular deformation or rotation, you will develop a corresponding force or a corresponding moment. So in this particular case, you're allowing the rotation, so the corresponding moment will not develop, right? So for these cases, at this end your bending moment will be 0, at this end also your bending moment will be 0. This is, however, not true if the pin is somewhere in the middle. So suppose you have a pin, suppose you have an overhanging beam which may be looking something like this. Suppose you have a beam where you have a pin support at the end, and say you have a roller support over here, right? At this support, m equals to 0. At this support also, the pin cannot take a moment. The m will be equals to 0, but here in the beam, not in the pin, within the beam, you will have a finite value of m. When we will solve some problems, you will get to see, right? Now, a third fundamental thing to make a note of is that now before moving on to the last thing which I was about to tell you. Now remember that although because of this applied loading, you will not have a moment at this this pin end or this roller end over here. If the external loading has a moment, then that moment will be developing, right? So you have nowhere to go in that case. For example, here if I come at this pin support and I have an externally applied moment over here, right, then that beam at that particular place will develop a moment. The pin will not, but the beam will. So in those cases, you will have the bending moments at the beam. Remember, we draw the shear force diagram and the bending moment diagrams for the beams, not the pins, right? It is along the length of the beam. So if there is no external moment at the pins or the rollers, and as long as the pins and the rollers are at the extreme ends, you will not have any bending moment, right? Now, another thing to note, that suppose you have a cantilever. So if you have a cantilever with a free end, as the name suggests, is free. That means that if you have the cantilever with some load, maybe a uniformly distributed load or a point load, the free end of the cantilever, it will have 0 shear, it will have 0 moment as well, because it's a free end, it cannot develop anything, right? This is again opposed to the case that if at the free end, suppose instead of having the free end like this, suppose at the free end itself you were going and applying a load over here, then your V in the beam will not be equals to 0. You will see that V becomes equals to that force that is applied. So if you are not applying anything particularly to the free end of a cantilever, your shear force and the bending moments are going to be 0. So these are some of the fun tidbits that you should remember while you are drawing the shear force and the bending moment diagram. All it helps you to do is to catch some errors. So suppose you have drawn the shear force diagram or the bending moment diagram, and you see your beam is simply supported, or it has a pin at the very end. It need not be simply supported. If it has a pin at the ends, at both ends of the beam, you have the pins, and you see after you have found the shear force diagram and the bending moment diagram, suppose the bending moment has a finite value at the end, that should tell you then and there that something is wrong, that you're at the ends. If you have a pin or a roller, you cannot have possibly a bending moment unless of course an externally applied moment is there, which I showed over in this particular point over here. Similarly for the cantilever, if your cantilever end is free, that is at the end of the cantilever you do not have an applied force, or for that matter if you do not have an applied moment over here, then in this particular case also your M is not equals to 0. But suppose at the end you have no moment and you have no applied force, then in that particular case you will have the case where your V, because it's a free end, it's a completely free end, you're not applying any external forces over here, then you will have the V equals to 0, M equals to 0 over here, right? So these are some of the things to always keep in mind while you are deriving the shear force diagrams and the bending moment diagrams for beams under the different kinds of loadings, right? So now that we are more or less set with the convention, the positive convention, and also some of the tidbits, we will go ahead and look at some of the example problems. And shear force diagrams and bending moment diagram problems are such that you can make n number of problems for that. You can take a beam, you can put any different kinds of loadings, and you can try to solve the shear force diagram and the bending moment diagram. What we'll try to do is that we'll try to look at many different types of problems, and the more number of problems you will do, the more thorough you will be with drawing proper shear force diagrams and bending moment diagrams.